Okay, ethanol plus one water?
Yeah. Then it yields acetic acid. Plus 4 hydrogen plus 4 electrons.
Okay. Once we get the half reaction, there's a way to check if the half reaction is correct. Do you know how to check to see if this is correct or not? We can't look it up in a book or a chart, but we can do this.
Can you just count the atoms?
Yeah, we'll count the atoms first. 2 carbons, 3, 5, 6, 7, 8 hydrogens, 3, 4, 4 plus 4 is 8 hydrogens. 2 oxygens, 2 oxygens. Okay, so the atoms are balanced, but we also have to check one more thing. What is that? The charge. So ethanol is 0 charge, water is 0 charge, acetic acid is 0, H is positive, so we have 4 positive and 4 negative charges. Those cancel each other out. So 0 charge on the left, 0 charge on the right. And so this checks out. This looks good. So that's the way we're going to check it. Okay, then what did you do? You combined these two?
Yeah.
Okay. When we combined the two, did you multiply by any?
No, because the electron, there's 4 electrons.
Yeah, there's 4 electrons here, 4 electrons here. That's good. Just stand it up. What did you get? You got ethanol plus
H2O.
plus H2O.
O2.
Plus O2.
Can you leave out the hydrogen or get that?
Okay, yeah, the 4 hydrogens here, the 4 hydrogen ions here, so the H ions, they cancel. The electrons, they cancel too. Okay, and then what?
Use the acetic acid.
Well, I guess we could put the 4 hydrogens in here. 4 hydrogens. This goes to
The acetic acid.
acetic acid
2 water molecules.
plus 2 waters plus 4 hydrogen, 4 H pluses. All right, so this would be the combined here, and then the final step would just be to simplify it. We can see that there's some spectators here. For example, the 4 H pluses here cancel out the 4 H pluses here. I have 1 water here that'll cancel out one of the 2 waters here, and they'll just leave me with 1 water there. Okay, that looks like it. We want to just take a look at the driving force. There was definitely a driving force here, otherwise the wine would have not turned into vinegar. So there's definitely a driving force here, but let's see what it is. So what we do here is we just look. Our oxidizer is going to be oxygen and H plus. Our reducer is going to be, the conjugate reducer would be water. Our reducer here is the ethanol and water. Our oxidizer here would be the acetic acid. So when we label this, the ethanol is our reducing agent, oxygens are oxidizing agent. Acetic acid would be our conjugate oxidizing agent. And water here would be our conjugate reducing agent. And so what's a better oxidizing agent? O2 or acetic acid? O2 or acetic acid? If you can't tell there, look at the reducing agents. What's the better reducing agent? Ethanol or water? Ethanol. And so we're going from stronger reducer to weaker reducer. If that's the case, then the oxidizers must be the same. Oxygen must be a stronger oxidizer. Acetic acid is a weaker oxidizer. And so this is our driving force here. And so we can simplify it. We can just erase out the water there, and our net equation is going to look like this. That is the ethanol plus the O2 yields the acetic acid plus H2O. That would be the reaction. balanced redox reaction. All right, so that's the chart method using skeleton redox. Typically with skeleton redox, we have reactions that don't appear on the chart. If we go back to chapter 19 is where they talk about redox here. Let's look at the next one they did here. They did permanganate is a strong oxide reagent that oxidizes chloride to chlorine in an acidic solution. Manganese ends up as monatomic manganese 2 ion. So permanganate goes to manganese 2, and chloride goes to chlorine. So write the net ionic equation, and that's what we get when we do the chart method. We get the net ionic equation. So this is it. This is the skeleton. This is the overall reaction, but this consists of 2 halves. And the first half is permanganate goes to manganese 2. The second half is chloride goes to chlorine. I've seen chloride goes to chlorine. That's on the chart, isn't it? That is on the chart. Chlorine goes to, chlorine plus 2 electrons goes to 2 chlorides. We've seen that on the chart. And so we could reverse that. And so I don't need to use the skeleton redox because I have it on the chart here. If I look at the chart, here, I see 2 chlorides can go to chlorine plus 2 electrons. So I can just reverse this reaction here. So I don't need, I can just copy that off the chart. Here. And so that's what they did. They copied it off the chart. 2 chlorides goes to chlorine plus 2 electrons. So that takes care of chloride. But what about permanganate? Does permanganate appear on the chart? Actually, permanganate appears on the chart too. Does the permanganate on the chart go to manganese 2 plus? That's what we need to confirm. Because it might not be, you know, it might be more oxidized or less oxidized, so depending on the condition. So this is permanganate goes to manganese 2. So let's go back to the chart and take a look. And so here we have permanganate. Permanganate goes to manganese 2. Permanganate plus 8H plus 5 electrons goes to manganese 2 plus 4 waters. We have that on the chart. And so since both of these are on the chart, we can just use the chart method for this. We don't need the skeleton redox method for this. We don't need to do the skeleton redox method for this because we have this. So this is the first half reaction, the half reaction that produces electrons. We want the half reaction that consumes the electrons. Well, they aren't showing it here, but we can just copy it down on the chart. But they aren't doing it. They're doing the skeleton redox. They balance all elements other than oxygen and hydrogen. The manganese is already balanced. And then they balance the oxygens by adding waters. And then they balance the hydrogens by adding H+. Then they balance the charge by adding electrons. So after going through all that, they came up with this equation. Permanganate plus 8H plus 5 electrons yields Mn2 plus with 4 waters. Didn't we just see that? And so this one, they didn't have to do that. They could have just copied it from the chart, which is fine. The ones that don't appear on the chart, those are the ones you have to do using skeleton redox. So this was showing skeleton redox for examples that don't even need skeleton redox. And then they added up the 2 half reactions to get the net. So this is the net. Here. And that's the end of the chapter. All right, so what we're going to do, well, that's redox, and that's basically it for what I was going to say about redox. And so we covered them. We covered metathesis, acid base, and redox. Only Bronsted acid base. We didn't cover Lewis acid base. Okay. let's just do some general reactions examples. All right, the first example is HCl. Tell me the chemical properties of HCl. What are the chemical properties of HCl?
Strong acid.
This is a strong acid. That's correct.
Soluble in water.
Okay, soluble in water. That would be a physical property, but that's an important property. It's soluble. It's a strong electrolyte. That would also be a physical property. But those are important. Those help with the chemical understanding of chemical properties of it. So for chemical strong acid, what else can you say about HCl? It is a strong acid. It's one of the 7 common strong acids you memorize. Is that it for chemical properties? It is a mineral acid. Yeah, that's true. It's a mineral acid.
Is it not too
I'm sorry?
late? Is it not too late?
Oh, one more time. Sorry.
Not too late, sir?
It's an oxidizer. Yes, it's an oxidizer. It's an oxidizer, but it's not an oxidizing acid. That's true. It's an oxidizer. It's also a reducer, not a very good reducer. It's also a base, but not a very good base. So basically, it boils down to this. What we want to do is we want to approach this one systematically. How many different types of reactions are there? Most people will say, okay, it's a strong acid, but we should look at all 3 reaction types. What are the 3 reaction types? First, we look at metathesis. If we look at metathesis, then we have hydrogen ions and chloride ions. Hydrogen ions and chloride ions. Hydrogen ions hydrogen ions like a lot of ions. And so we're going to talk, hydrogen ions is acid, so we'll talk about this more in maybe the acids part of things. Well, what about chloride ions? What cations does chloride like to react with? Can you think of any cations that chloride will want to react with? Silver. Silver ions. Chloride likes silver ions, yeah. So any kind of silver salt, like silver nitrate, silver acetate, silver chlorate, if I mix the and solution contains silver ions, we're going to precipitate out silver chloride. What else? Lead, 2, and mercury 1. And so chloride, HCl will react with any salt that contains silver ions, lead ions, or mercury 1 ions in solution. And so HCl will undergo metathesis reactions with silver, lead, and mercury ions. Then we go to acid base. H plus is a good acid. H plus is also known as what? H plus is known as a proton. It's all in aqueous solution. It's also known as hydronium, H3O plus. So it's a strong acid, H plus or hydronium. And so what bases will hydronium react with? So let's take a look at the bases here. So this is, I'm going to just show you how we use this chart. Do things quickly. So I'm interested in what bases. Will hydronium ions react with any base? So for example, I know it's a good strong acid. Hydronium ion, will hydronium ion neutralize chloride? Will it react with chloride? If hydronium or H plus reacts with chloride, what's formed? Well, hydronium is the acid. Acids donate a proton, bases accept a proton. So if hydronium donates a proton to chloride, you know what forms? Hydrochloric acid. So is that favorable? If we go from hydronium to hydrochloric acid, are we going from a stronger acid to weaker acid, or weaker acid to a stronger acid? We're going from a weaker acid to a stronger acid. Is that driving force? No. No. But what about this? What if I did hydronium? If hydronium reacts with sulfate, to produce hydrogen sulfate ion or bisulfate, is that favorable? And so here, when I compare it, I take hydronium, that's my acid, sulfate's my base. So I donate a proton to the sulfate, and then I form HSO4 minus. Now I compare this acid with this acid. Which one's stronger? Well, hydronium's stronger, bisulfate's weaker. Therefore, that should be driving force. That's favorable. And so this is what it turns out to be. What we can say is that hydronium will react with any base stronger than water. Any base stronger than water. Any base weaker than water, there's no driving force for. And the water would be the cutoff here. And so H plus reacts with all bases. Stronger than water. And so that means this one, it'll react with this one, which is called trichloroacetate, react with sulfate, dihydrogen phosphate. This one, which we'll skip the name of. What's this one? You should know the name of NO2 minus. Nitrite. What is it? Fluoride. Fluoride. This one's called formate. This one you should know. Below formate is acetate. This one, HCO3 minus, is called bicarbonate. HS minus is called this is just the hydrogen sulfide ion, or bisulfide. This one is the hydrogen phosphate, or monohydrogen phosphate ion. This one is ammonia, cyanide, carbonate. Sulfide. Amide. Good. Oxide. Hydride. This one's called methide. Methane forms methide. And so those are all the bases on that chart that are stronger than water. We'll react with all those. Now, chloride is a base. Chloride is a base. But basically, chloride will react with any acid stronger than HCl, but because of the leveling effect, nothing's going to happen. The leveling effect causes all these acids to be equivalent to hydronium. And so chloride is too weak. We call too weak to be a base. And so it's negligible. Base properties are negligible. So we'll put a little asterisk here, base, but base properties are negligible. So if you run out of acid, you can't grab a bottle of table salt, you know. Table salt has chloride, yes, and chloride is a base, yes, but it's too weak. It's not going to do anything to neutralize your acid in your stomach. And so chloride's kind of what we call neutral. Technically it's a base, yes, but it's practically neutral.
Okay, finally we get to redox. When we get to redox, we know that H plus is what? A proton, and is it an oxidizer or reducer?
Or both. H plus, oxidizer, reducer, or both?
That's an oxidizer.
It only occurs on one side.
Plus is an oxidizer.
Well, if H plus is an oxidizer, what will it oxidize? Will it oxidize everything? If this is an oxidizer, it should oxidize everything? No, what will it oxidize? Tell me what it will oxidize. Or give me a list or tell me what it will oxidize. Well, I mean, this is the same type of deal. It will oxidize reducing agents. Well, here's a list of reducing agents. Will H plus oxidize copper? Will H plus oxidize copper? If H plus oxidizes copper, what would we form? We'd form copper 2 plus, right? Copper would lose electrons. And so if H plus oxidizes copper, we form copper 2 plus. Well, which one's stronger? Copper 2 plus or H plus? Copper 2 plus is stronger. And so what we're going from a weaker oxidizer to a stronger oxidizer. Is that favorable? No. And so H plus will not oxidize copper. Will H plus oxidize tin too? Will H plus oxidize this? What's this called? Yeah, this is kind of weird because H2S, normally we name it by its binary molecular name. Binary molecular name would be dihydrogen monosulfide, but since this is also an acid, we name acids in the molecular form as ionic compounds, so we call this hydrogen sulfide. But we just saw hydrogen sulfide earlier, it was HS minus. That's called hydrogen sulfide ion, this is just called hydrogen sulfide gas. Well, H plus can't oxidize that. Can H plus oxidize H2? Not really, because it'd be a tie, you know, H against H. Can H plus oxidize lead? Yes. If H plus oxidizes lead, what do we form lead 2 plus? Which one's stronger? Well, H plus is stronger than lead 2. So we're going from stronger oxidizer to weaker oxidizer. And so what does H plus oxidize? It oxidizes lead, tin, iron, zinc, aluminum, magnesium, sodium, calcium, potassium, lithium. What won't it oxidize? It won't oxidize H2S, SN2 plus SO2, Cu, iodide, SO2. Didn't I see that before? SO2 is a... Where did I see that before? SO2. Sulfur dioxide. You remember where you saw that? I saw that as a reducing agent. The truth about sulfites in wine, the myth of the red wine headaches, contains sulfites. These are words you see on almost every bottle of wine. Just 2 little words. What are sulfites? The term sulfites is an inclusive term for sulfur dioxide, a preservative that's used in winemaking. For its antioxidant and antibacterial properties, SO2 plays an important role in preventing oxidation and maintaining a wine's freshness. This is the antioxidant. But is even though it's an antioxidant, is H plus strong enough to oxidize that antioxidant? Yes, SO2 is an antioxidant, but is H plus strong enough to oxidize that antioxidant? No, we need a stronger one. Unfortunately, there is a stronger one. What is that stronger one? Oxygen, which is a way here from left. Here, oxygen has no problem oxidizing SO2. SO2 is going to be a better antioxidant than ethanol. Ethanol is in this region, flammability.
That's why oxygen is your enemy when you're making wine.
Yeah, I think so. Although, you know, it does create some flavors, you know.
Madeira.
Yeah. But let's see. All right, so H plus is an oxidizing agent. It's going to oxidize, will oxidize. Reducing agents stronger than what? Will oxidize all reducing agents stronger than H2. Interestingly, there's a chloride, and chloride is what chemically? A base, but it's also a. Didn't we just see chloride on this chart earlier? Chloride is also a reducer. And so HCl is both an oxidizer and a reducer. Just like it's both an acid and base, but its acid properties are much stronger than its base properties. When we look at HCl, well, what's stronger? Are the oxidizing properties of HCl stronger than the reducing properties of HCl? Because HCl contains a reducer, chloride, and an oxidizer, H+. And so we look at chloride. Well, one thing we can tell is chloride a very good reducer based on its position in the chart? No, it's an awful reducer. In fact, in order to oxidize chloride, you would need an oxidizer. Like, for example, dichromate is a powerful oxidizer. Is dichromate powerful enough to oxidize chloride? If dichromate oxidizes chloride, we form chlorine. Well, which one's stronger? Well, chlorine's stronger than dichromate, so that's not favorable. And so dichromate will not oxidize chloride. That means chloride's really hard to oxidize. What do we need to oxidize chloride? We need something like this. What's this called? Permanganate. Permanganate's strong enough. If permanganate oxidizes chloride, we form chlorine. Well, permanganate's stronger than chlorine. This is lead 4 oxide. We want to avoid lead compounds. Lead 4 oxide will oxidize it. This is, and so what reacts with chloride? Well, fluorine will. Well, fluorine reacts with almost everything. Tell here, I mean, everything on this chart. Ozone, S2O8 2-, hydrogen peroxide, permanganate, lead 4 oxide. All those species will react with chloride. We can list them, or we can just say chloride will reduce. Chloride's a very weak reducing agent. And so chloride will reduce oxidizing agents stronger than chlorine. There aren't that many oxidizers that are stronger than chlorine. Okay, so this is the systematic approach to chemical properties. So we'll stop here, we'll take a break, and then do a couple more examples.